All right, so we're back, and let's continue and see how we would deal with the other set of rectangles that are outside or greater than our region that we're trying to find. So this is a little bit harder. The left-hand endpoint formula is a little bit harder to see. And so the left-hand endpoints of all 5 intervals are going to be 2/5 times the quantity I minus 1, where I is equal to 1, 2, 3, 4, and 5. Still, the width of each interval is 2/5, and so what we'll do is we'll add up, and I'm skipping a little bit of discussion because your ability to set this up in the way I'm doing is not really going to be something we're messing with. This left-hand rectangle is the harder of the two, so that's why I'm going to skirt by some of this discussion, just show you the thought process, and then just get results and go from there. Okay, so this will, our height of our rectangle again is y, and this time, because the function is hitting on the left side, it's this x right here that we're concerned with. The height of the rectangle therefore is going to be y, which is f of x sub I, where this is your x sub I that's producing that height. And of course the width in this is 2/5. That's the width of that rectangle. And if we were to, I'll do the first step of this and then not go through the algebra, because this is a little bit more complicated than I really anticipate you're having to deal with. So if we substitute that in, that will be 2/5 times I minus 1 squared oops, I wrote that square the wrong place. Hold on, let me back up and fix that. Oh, it's not going backwards. What's going on here? Can't undo that for some reason. Oh, there we did. Okay, sorry about that. So that's our x sub I is the 2/5 of I minus 1 squared plus 5 multiplied by our 2/5. And if you just trust me, after you do all of this algebra, you will get a result of 202 over 25. And this result is, as you can see from the picture above, it's too big. So this is greater than the actual area that we're looking for. And our earlier answer, which was, let me look back at that, 162 over 25, is smaller than our actual area, which means that our actual area lies between these two values. That tells us, if we go to decimal form, that 6.48 is less than the actual area, and that's less than 8.08. The way to get a better approximation than that would be to increase n from 5 rectangles to a larger number of rectangles. All right, so now if you look at a generic problem that we could encounter, instead of this very specific one with a particular function in mind, we could, for example, have something that looks like this. Let me move this down a bit. We could have just some generic function, y equals f of x, from x equals a to x equals b. And we want to know the area of this region. And so, as I said earlier, what we'll do is we will think about there being rectangles, and I'm going to draw one representative rectangle, and I'm going to draw it pretty wide so we can see it. But that's the rectangle that's going to represent the idea. Now, the rectangle could be touching the curve on its left-hand side or on its right-hand side. Doesn't really matter according to the theory that we're going to be using. And let's just say that we are trying to find the area by, first of all, let's calculate the width of this rectangle. That, as I said earlier, is going to be generically b minus a, which gives you the width of the entire region, divided by n, the number of rectangles. So once we have that established, then we can assume that there's a x value, we'll call that little m sub I for the ith rectangle. There's some x value that will create the smallest or minimum y value for the ith rectangle. Okay. We can also assume that there's probably some maximum value that's achievable. So there'll be some x, we're going to call that x capital M sub I, which will create the maximum possible y value on that subinterval for that rectangle, in other words. Again, for the ith rectangle. So, if we were to multiply that height that we get using the minimum value possible times delta x, that would be the area of the smallest rectangle possible, and that will be less than or equal to the maximum y value you could get for that rectangle times the width of the rectangle delta x. And we can call this one that we first identified, that would be the area of the inscribed rectangle, and this would be the area of the circumscribed in the second case. So in doing this, we're allowing ourselves to find that there is absolutely a largest and a smallest possible value for the area of that rectangle. And because of the extreme value theorem, is what's telling us that this maximum and minimum have to occur. Now, there is actually a height of that rectangle somewhere in that subinterval, some x value that will create the actual rectangles, the actual curves area. But at any rate, let me go on back to what we were saying. So there's something called a lower sum that's possible. And that's going to be represented with a lowercase s, which is the sum from the first rectangle, I equals 1, to the nth one. So we're assuming we have n rectangles. And this will be taking the y value that's minimum for each rectangle and multiplying it by the width of the rectangle, delta x, which is, of course, the area of the inscribed rectangles. The upper sum is very similar. We'll call that capital S sub n. And that's equal to the sum from the first rectangle to the nth one of the height of the rectangle, which is the y value associated with the x capital M sub I that creates the largest y value possible for that rectangle, times the width of the rectangle, and that gives us the area of the circumscribed rectangles. Now, it should be clear to you that from our discussion earlier, the actual area of the rectangle is somewhere between the lower sum and the upper sum. So the lower sum is less than or equal to the actual area, which I'm just going to write area for it. The actual area is between the lower sum and the upper sum. Now, let's take this example that they give us on the next page, where f of x is equal to x squared, and we're going from x equals 0 to x equals 2, and see if we can find both the upper and lower sums for this problem. Notice this is a pretty simple function and not very complicated numbers, 0 and 2. So that's intended to make it easier to get the idea without making it extremely difficult. Okay, so delta x, which is b minus a over n, will be 2 minus 0 over n rectangles, which simplifies to be 2 over n. All right. So if you look at the picture of the inscribed and circumscribed, it appears that the inscribed rectangles are left-hand rectangles. So the left-hand side is determining the height of the rectangle. That's where the curve touches the rectangles on the left-hand side each time. Notice this is an increasing function, so that would always be true. If you had increasing then decreasing, that would not necessarily stay consistent. But again, this is a simplified example so that you can understand easily what's going on. So the left-hand endpoints are going to be the x value, little m sub I, will be 0, which is the left-hand starting point, x equals 0, plus I minus 1 times 2 over n, our delta x. Remember I said this was the more complicated formula. And so anyway, this ends up being 2 times I minus 1 all over n. So using the left-hand endpoints to find the lower sum, this is going to be sigma from I equals 1 to n of f of m sub I, lowercase m sub I, times delta x. This is sort of the generic formula. Now, more specifically for this problem, that's going to be sigma from I equals 1 to n of two times I minus 1 over n. Oops, sorry. Didn't mean to write that little blob there. See if I can get rid of it. Yep. Okay, so that's our x, and our function is the squaring function, so that squared, that's our height of our rectangle, times delta x, which is 2 over n. Okay, so let's go through and do some algebra to simplify this. It's notice even for this simple function, there's quite a bit of algebra involved, so make sure that your algebra skills are up to par here. All right, so doing a little bit of simplification behind the sigma first. Pen's having trouble working correctly here for a second. Let me see if I can, yeah, that's a little bit better. Okay, so the square of that will be 4 times I minus 1 squared over n squared. I distributed the squaring to all 3 factors, multiplied by 2 over n, okay, so that's going to end up being 8 over n cubed times I minus 1 squared, which is I squared, minus 2I plus 1. That's the square of I minus 1. Now notice that the 8 over n cubed with a index variable of I, 8 and n cubed are both considered constant, so I'm going to pull that out in front of the sigma. And also, the other thing I'm going to do in this step is go ahead and split. Oops, let me rewrite that a little bit better. I'm going to go ahead and split the sigma of that trinomial into separate sigmas. Sigma of the first thing, I squared, minus sigma of the second thing, 2I, plus sigma of our last term, the constant 1. All right, this does get to be algebraically pretty challenging. So we're seeing that here. Ooh, and I'm almost to the end of this page. I'm going to see if I can squeeze this in, finish this example. This is going to be 8 over n cubed. The I squared formula, if you'll recall, is n times n plus 1. It's supposed to be a parenthesis there. Times 2n plus 1. All over 6. Minus. Then that 2, I'm going to think of having pulled that out without actually writing that step. So I've pulled the 2 out. And then the sigma I that's left, if you recall, that formula is n times n plus 1 all over 2. Plus, then this is the sigma of a constant. That formula is the constant 1 times the upper bound n. So if you do some simplifying, which unfortunately I'm not going to have room to show you here. So if you want me to do this later in class again, when we're talking later, I can certainly show you this algebra as needed. But, oh, I'm sorry, I started just copying what I already had because I was trying to talk and write at the same time. All right, so that ends up being 4 over 3n cubed times 2n cubed. You can imagine how much algebra was involved in simplifying it down to this point, minus 3n squared plus n. And then if you distribute, you will get 8/3 minus 4 over n plus 4 divided by 3n squared. Okay, that's a good place to stop. That is the lower sum as we've just calculated.